right, go and open up your notebooks now to the Theorems Corollaries section. Theorems Corollaries section, Theorem 61, it's a big one. This is the theorem that's going to lay the groundwork for the Pythagorean Theorem, undoubtedly the most famous theorem. Now, not the one we use the most this year, right? Side angle side, I would say, is probably the most used theorem this year. But the most famous theorem, in fact, a theorem that you would have probably learned about when you were in junior high, right? What does the Pythagorean Theorem say, Quentin? Yeah, great memory. C squared equals a squared plus b. Okay, we were talking about that before we started the video. C squared equals a squared plus b squared. He knew it before, I'm sure. But anyway, yeah, the hypotenuse square equals the square of each of the legs added together, all that. Well, that theorem comes about because of Theorem 61. It's a big one in a couple of ways. One, it's big in importance. Number two, it's big in length. Because there's three parts to this theorem. If you're going to write this down, Theorem 61 says this. If, comma, in a right triangle, comma, if in a right triangle, the altitude is drawn, if in a right triangle, the altitude is drawn from the vertex of the right angle, if in a right triangle, the altitude is drawn from the vertex of the right angle to the hypotenuse, altitude is drawn from the vertex of the right angle to the hypotenuse, dot, dot, dot. Go down to the next line, Roman numeral 1. Three things. Roman numeral 1. The two triangles formed are similar to each other. The two triangles formed are similar to each other and to the given right triangle. The two triangles formed are similar to each other and to the given right triangle. So let's get the picture of what we're talking about here real quick before we move on to parts 2 and 3. If in a right triangle, okay, so we have a right triangle here, the altitude, that means perpendicular, is drawn from the vertex of the right angle to the hypotenuse. Well, you notice in drawing this line, I now have 1, 2, 3 triangles, correct? These two triangles we're going to prove are similar to each other, and they are both similar to the original triangle. That's basically what part 1 is saying. Make sense? Now, we know this. Once triangles are proved similar, we know the corresponding sides must be proportional, CSSTP. Those are what parts 2 and 3 deal with. Part number 2 says this, Roman numeral 2. The altitude is the mean proportional between the segments of the hypotenuse. The altitude is the mean proportional between the segments of the hypotenuse. The altitude is the mean proportional between the segments of the hypotenuse. So you'll notice when we draw this altitude, it turns the hypotenuse into a couple of segments. This length, whatever it is going to be the mean proportional between these two segments. So that segment is to altitude as altitude is to segment. That's part 2. Part 3. Part number 3. So again, we said if in a right triangle the altitude is drawn from the vertex of the right angle to the hypotenuse, then dot, 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 two triangles formed are similar to each other and to the given triangle. Part 2, the altitude is the mean proportional between the segments of the hypotenuse. Roman numeral 3, each leg is the mean proportional. Roman numeral 3, each leg is the mean proportional. Each leg is the mean proportional between the hypotenuse and the adjacent segment of the hypotenuse. Each leg is the mean proportional between the hypotenuse and the adjacent segment of the hypotenuse. Each leg is the mean proportional between the hypotenuse and the adjacent segment of the hypotenuse. So that this leg is the mean proportional between the hypotenuse and this segment that is adjacent to the leg, this segment of the hypotenuse, then this leg would be the mean proportional between the hypotenuse and the adjacent segment of the hypotenuse. That's what we're trying to prove. One thing that may help us a little bit is if we rotate the picture just a little so that our altitude comes down this way. Turn to the proofs of theorem's corollary section. New sheet of paper in the proofs of theorem's corollary section at the top of the page, theorem 61. In right triangle, altitude to hypotenuse. In right triangle, altitude to hypotenuse, Roman numeral 1, we're proving there are 3 similar triangles. Roman numeral 2, we're proving that the altitude is the mean proportional between the segments of the hypotenuse. So we're trying to prove that segment 1 is to altitude as altitude is to segment 2. And number 3, we're trying to prove that each leg is the mean proportional between a segment of the hypotenuse and the hypotenuse as a whole. But since there are 2 legs and 2 segments, times 2. It's kind of how we're going to abbreviate theorem 61. So a lot of head work on this theorem. Again, it's big in the sense of important. It's also big in the sense of there's a lot to this one. Again, this is what paved the way for the Pythagorean theorem to come so easily later. So if you would, maybe next to, since this doesn't take up a lot of room horizontally, but it takes up a lot of room vertically, let's go and draw our picture. Go ahead and draw to the best of your ability a right angle coming down and then connect across. Try to draw a right angle coming down, then connect across so that we get a right triangle. Let's call it ABC, where C will be my top vertex, and we'll call our altitude CD. While we're setting up our picture, let's go ahead and number these 2 angles 1, 2, 3, 4. Let's go and number these angles 1, 2, 3, 4. This will make our life just a little bit easier in completing the proof. All right, once you got that down, let's go and get down our given. Well, it says that if in a right triangle, so we have to be told we're starting with a right triangle. So right triangle, ABC, with right angle C. So we're given a right triangle, which means we have a right angle. Let's specify that the right angle is at C. We said if in a right triangle, the altitude is drawn from the vertex of the right angle to the hypotenuse. So we're told that CD is the altitude. And altitude CD. Altitude CD. That's our given. Then it's all the then this is true, then this is true, then this is true, then this is true. So what are we going to prove? Well, let's go ahead and put the first statement out here. Proof, first of all, that you've got 3 similar triangles. Well, name one of my triangles. Audrey? ACD. ACD. So we want to prove that triangle ACD is going to be similar to another triangle, which would be, Kendall, BCD, but I happen to know we're going to want to say CBD. So we're going to modify the lettering just a little bit there, which is also going to be similar to the given triangle, which would be class ABC. So we're going to want to prove that triangle ACD is similar to triangle CBD, which is similar to triangle ABC. Now you realize that's really the crux of the proof. Because what I'm trying to prove next are proportional pieces, right? Well, if triangles are similar, then the proportional pieces should fall into place just fine, shouldn't they? By CSSDP. We're going to get the triangle similar by angle. Once we've got them, CSSDP should take care of all of this. But we need to figure out how in letters we're going to state it. So we want to prove, second of all, that segment is to altitude as altitude is to segment, referring to the 2 segments of the hypotenuse. Well, my first segment, of course, is AD, is to the altitude CD, as altitude CD is to the other segment, BD. So that's the second thing we want to prove. that AD is to CD as CD is to BD. And number 3, I'm going to have 2 of these for each leg and adjacent segment. What I want to prove that a segment is to the leg it's adjacent to as that leg is to the hypotenuse. So for instance, we might start with segment AD is to the leg it's adjacent to AC as that leg AC is to the entire hypotenuse AB. And we want to do the same thing with the other segment, the other leg. So also BD is to BC as BC is to AB. It's a loaded proof. Once you have this down, 2 columns, statements, reasons, you may end up on the back side of this page by the time we're done, just because you're already probably halfway down the page by now. Okay, so not surprising if that's the case.
How many steps are there?
We're about to find out, aren't we? I don't know.
You'll find out.
45 steps.
All right, 2 columns, statements, reasons. Well, no, I don't think it'll be super long because we've already pretty much done our strategy, haven't we?
Yeah.
We want to get a bunch of angles equal, don't we? Get a bunch of angles equal, get the triangles similar, get the lines proportional CSSTP. No, I mean, the strategy's pretty well set. Just a matter of figuring out how to get all the angles we want. Fortunately, a surprisingly short given, right triangle ABC with right angle C and altitude CD. All right. Clang. Altitude. Let me say that again. Clang. Altitude. Altitude is clang. Altitude means we have a perpendicular. So what should I write for statement 2, Chris?
Altitude CD perpendicular to AB.
CD is perpendicular to AB. Reason, Chris?
Definition of altitude.
Definition of altitude.
Feel attacked.
All right, okay. Number 3. If it makes you better, that's all that matters. All right, number 3. Perpendicular. Clang. Genesis. Oh, you're 1 step too quick. And angle 3. So angle 3 and angle 4 are right angles. Reason, Genesis.
Definition of perpendicular line.
Now number 4, Genesis, you wanted to go here a moment ago. Why not? We could say that.
Angle 3 equals angle 4.
And why stop at those 2 right angles when we've got another one up here, right? Why not get, since we want 3 similar triangles, let's get all 3 of them equal. So let's state number 4 that
Angle 3 equals angle 4 equals angle C.
because,
All right angles and right.
good, or they don't even have to technically be in right triangles to be equal. All right angles are equal. So that gives me some angles. Now, again, 3 and 4, those are the D angles right here. And obviously C is the C angle there, correct? So that's, in these triangles, that's one of my angles that I need for angle.
Angle 1 and 2, are they equal?
That's a good question. Are 1 and 2 equal, class?
It's perpendicular, so when it cut off the vertex angle in half?
Does a perpendicular necessarily bisect the vertex angle? It would if this were an isosceles triangle, right? Perpendicular does bisect the vertex angle in an isosceles triangle, and by the way, bisects the base. But I don't know that this is isosceles. I know that it's right, which again, that's not mutually exclusive, right? You could have equal legs and a right angle at the top, couldn't you? But I don't know that it is. So no, I don't know that 1 and 2 are equal to each other.
Well, can we say angle D equals this? No.
Angle B.
Angle
B.
Okay, as far as these 2 triangles are concerned, angle B and angle B are equal to each other. That would take care of these 2 being similar.
Can I
Thoughts on maybe, what about maybe these two?
C, angle C would equal angle C.
Careful. ACD, you're looking at angle 1 technically. BCD, you're looking at this angle C. Ooh. Do you see the problem? Yeah, I mean, if I were even looking at these two, I could say angle A equals itself by identity, and that would be these two, but that doesn't take care of this guy. Somehow there's, So here's the thought, here's the direction we're gonna go. I know I've got right angles, which means both of these triangles, class, are right triangles. Let's go ahead and state that for number 5. That triangle ACD and triangle CBD are right triangles. And we know they're right triangles, Kendall, because we have right angles. 3 and 4 are right angles, therefore these are right triangles based on the definition of right triangles. And if you have right triangles, coming back to a statement we need to have memorized very well, in any right triangle class, the two acute angles are complementary. So let's think for just a moment about this little ACD triangle. Which angles must be complementary, class?
2 and B and A.
No, in this right triangle, right here, which angles must be complementary?
1 and A.
1 and A. Angle A and angle 1 are complementary. We know this, Ethan, because
What definition?
Jamie?
If two acute angles equal.
Oh, I just said it. The two acute angles in a right triangle are complementary. Good, Genesis. The two acute angles in a right triangle are complementary. Say that with me, class. The two acute angles in a right triangle are complementary. But of course, ACD is not the only right triangle. BCD is a right triangle. Okay, so what two angles do we know are complementary, class? Angle 2 and angle B. So angle B and angle 2 are complementary for the same reason. Still part of statement 6. But that's not the only other right triangle. I've got 3 right triangles, remember? I've got ACD, I've got CBD, and I've got ABC, the whole thing. Which angles are complementary in ABC? A and B. For the same reason, angle A and angle B are complementary for the same reason. Now let's lock in on statement 6. A and 1 are complementary, B and 2 are complementary, A and B are complementary. I'm sorry?
1 and 2 are complementary.
Okay, we could add that statement as well if we wanted to, Quentin, that 1 and 2 are complementary, but that would be, we'd have to say the whole equals the sum of its parts, C equals 1 plus 2. Since C has already been defined as a right angle, therefore 1 and 2 are complementary based on definition of complementary. I don't think we need that, but I'm not positive. We may come back to that. Let's just look at what we've got in 6, though.
If A, so that means angle A equals angle 2.
Good, because yeah, A and 2 are both complementary to B, correct?
Correct.
And complements of equal angles or of the same angle are equal. So number 7, since 2 and A are complementary to B, angle A must equal angle 2 because complements of the same angle, or of equal angles, but that doesn't apply right here, are equal. Complements of the same angle are equal. Let me move this further out of the way.
As well as B and 1.
Similarly, yeah, B and 1, because B and 1 are both complementary to A. So angle B must equal angle 1, because complements of the same angle are equal. So looking at these two triangles, equal, 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 the two side triangles must be similar, class, by angle, 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 even if technically, since we did go to the trouble to get that. So number 8, triangle ACD is similar to triangle CBD. We've got 2 of them similar by angle, angle. I'm not going to write the third angle just in case I don't want to mess things up later. Well, let's think about this for just a minute. What about CBD and the whole thing? Angle B equals angle B. You know what? Let's sneak this in. Can you squeeze something in here and say like 7B? Angle B equals angle B by identity. We talked about it and then we never actually wrote it down. So I'm going to sneak it in here. 7B, angle B equals angle B. You could write it under and draw arrows. By identity. Therefore, also by angle, this whole thing must equal this because we have B equal to itself. We already said that C and 4 were equal. What about the side and the whole thing?
It's also similar to it as well.
Right. So the whole thing is similar to this side.
And the other side.
How is the whole thing similar to this side?
Because it's similar to, so if triangle CBD is similar to the whole, and then ACD is also similar to CBD.
So you're saying triangles similar to the same triangle are similar to each other? Have we ever proved that?
Why not?
We haven't proven it. We haven't needed to, frankly. It is true, though. It is a true statement. It's just not something we've proven. But we could easily prove it this way. Just as we said B equals itself in this side and the whole thing, so with this side triangle class, we could say that angle A equals itself. Let's sneak that in as well. That way we don't have to work a whole other proof in to prove something when we can just add one little statement in the identity. So yes, therefore ACD is similar to ABC, and triangle CBD is similar to ABC. All of these true by angle. And again, the first one technically by angle, but I didn't want to make a new statement. So we got a whole lot of similar triangles, and then yes, since AD is similar to CBD, and ACD is similar to ABC, and CBD is similar to AD, they're all just 3 similar to each other. So part number 1, check. All right, now, let's get to part 2. You know what, I'm going to move this, for sake of space, to over here. A, B, C, D. Number 9. I want to find a way to prove now that AD is to CD as CD is to BD. Thoughts on how I could prove that that proportion is true, Jamie?
Well, if we have similar triangles, are the sides already proportional?
Okay, if we have similar triangles, sides would be proportional. What 2 triangles do we really need to be similar here, Jamie?
ADC and CBD.
ADC needs to be similar, you said, to
CDB.
CDB. Do we know that ADC and CDB are similar? Right there. So, is this proportion true, class? By CSSDB. So number 9, AD is to CD as CD is to BD by CSSDB. Check off number 2. All right, let's come to number 3. I want to prove that this proportion is true. What would have to be true for that proportion to be true? Ethan?
For triangles ABC and similar to triangle ABC.
Do we know that ADC and ACB are similar?
Yes.
Yep, right here. So still part of number 9, AD is to AC as AC is to AB, still by CSSDB. All right, that's half of number 3 checked off. All right, let's take a look at the last one. What would have to be true for BD to be to BC as BC is to AB? Chris?
Triangle CBD would have to be similar to triangle ABC.
Yep, and that's what we've got right there. So sure enough, that last part is also true that BD is to BC as BC is to AB, and everything is now proven. Questions on this proof? Questions on this proof? All right. Turn to the class notes section now. We're going to put this in your pictures and proportions section. So let's find where you left off with your pictures and proportions. If you would, go ahead and draw, again to the best of your ability, a right triangle with an altitude. Not an attitude, an altitude. That's like a mean right triangle. It's got altitude. All right. Dumb math jokes. All right. I want you to label segment 1, segment 2. I want you to label altitude. I want you to label leg 1, leg 2, and I want you to label hypotenuse. So we have 2 legs, we have hypotenuse, and we have 2 segments of the hypotenuse formed by this altitude. Roman numeral 1, 3 similar triangles. Roman numeral 1, we have 3 similar triangles. Roman numeral 2, segment 1 is to altitude as altitude is to segment 2. Roman numeral 3, segment is to leg as leg is to hypotenuse times 2. Segment is to leg as leg is to hypotenuse. And again, that means that segment 1 would obviously be to leg 1 as leg 1 is to hypotenuse, or segment 2 is to leg 2 as leg 2 is to hypotenuse. 2, or really 3, mean proportionals that we have here. Now, we're not going to use the sub-notation necessarily here, but let's go ahead and say these proportions together as I pointed on the class. Starting with number 2, class. Segment is to altitude as altitude is to segment. Again, segment is to altitude as altitude is to segment. One more time.
Segment is to altitude as altitude is to segment.
Good, and then for our other proportion, we've got, say it with me, segment is to leg as leg is to hypotenuse. Again, segment is to leg as leg is to hypotenuse. So, again,
segment is to leg as leg is to hypotenuse.
And
segment is to leg as leg is to hypotenuse.
Good, it's the same thing, it's just looking at a different segment and leg that time because there's 2 segments, 2 legs. Make sense? That's the proportion you need to memorize goes with this picture. Now, a word of caution. Chris actually already mentioned it because he thought he had an angle bisector up there. Notice the angle isn't marked as being a bisector, but it does look, doesn't it, very similar to this picture. Do you see the difference? Here we have an altitude marked and a right triangle. Here we do not have an altitude, nor is it a right triangle. Here it's segment is to segment as side is to side. Here it's segment is to altitude is to segment. Segment is to leg is to hypotenuse, and segment is to leg is to hypotenuse. They look similar. You've got to keep them separate. Bisected angle, segment is segment, side is to side. Here we got the mean proportionals. Make sense? All right, turn over to page 210 in your, you know what? We'll save that. We'll save that. We don't have time to get into those problems. Now, I do want to go through Corollary 61.1. Let's just round out the notebooks. So we'll save that for next lesson. It's been a little longer going over the exam than I planned. Corollary 61.1 in your theorems corollary section. We obviously will not do the proof. We will talk through the proof. Corollary 61.1. If a perpendicular is dropped from any point on a circle, if a perpendicular is dropped from any point on a circle, if a perpendicular is dropped from any point on a circle upon a diameter, perpendicular is dropped from any point on a circle upon a diameter, comma, then the perpendicular is the mean proportional between the segments of the diameter. Then the perpendicular is the mean proportional between the segments of the diameter. If a perpendicular is dropped from any point in a circle upon a diameter, then the perpendicular is the mean proportional between the segments of the diameter. We have a circle, we have a diameter, we have a random point here, I don't know. And from any point on a circle, we drop a perpendicular to the diameter. We want to prove that perpendicular is the mean proportional between the segments of the diameter. So that segment is to perpendicular is to segment. Thoughts on how we might prove this corollary?
Use theorem 61.
Use theorem 61 for sure, right?
Are the mean proportionals equal?
I'm sorry? Which auxiliary lines?
To form a triangle.
Yeah, because if we have a diameter class, then we also have a semicircle. And any angle inscribed in a semicircle is a
Right angle.
right angle, which means we have formed a right triangle, which means this perpendicular could be called an altitude, and segment is to altitude is to segment. So very easy proof based off of theorem 61. All right, no homework this evening. We will be reviewing over this and practicing with this in our next lesson. Have a wonderful rest of your day, and you are dismissed.